In this three-part series, we're going to be talking about rate laws and integrated rate laws and how they come about. Now, this is for someone who has maybe learned these things before, or maybe not learn these things, but have a general idea of rate laws and stuff like this. Maybe you're taking like AP chemistry or one of the other divisions that are kind of a higher level of chemistry, because today we're going to be getting into some pretty mathematically complex topics here. Differential equations, right? And I'm going to try and explain it for those who have never taken the class before, never even maybe taken calculus, right? We're going to try and explain it for every audience here, just so it can make a little more sense to you. So the rate of a reaction for a 0th order reaction basically says that, and I'm just going to draw a graph here, concentration has no effect on the rate. So how concentration is changing with respect to time is just linear. If I increase my reactants, it doesn't matter. It's always going to be moving down and it's not going to be affected, right? If it didn't, if I increased concentration or changed concentration, this would look a lot different. So basically, what I'm trying to get at here is that the rate of the reaction, is equal to some constant K, right? So there's the concentration of that reaction is not at all changing the rate of our reaction. Basically, if I have A plus B and it forms a new molecule C, right? Well, the synthesis reaction, if I increase A, the rate of the reaction is constant. It's not going to change, right? If I decrease B, it's not going to change the rate of the reaction. So when rate is equal to K, a 0th order reaction, we can write this as delta A over delta T equals K. Now what this is saying is it's the same thing, and we're going to have negative, because if this is reactants that we're talking about, reactants being consumed, the rate is negative, right? Because you're losing stuff, so you're subtracting it, negative rate. Hopefully that makes sense. So basically, we can rewrite the rate of a reaction where we're losing reactants as negative. Delta means change, so the change in the reaction, or the reactants, over change in time. So how much is the reactants changing over time? That's a rate. I hope that's a little bit easy to understand there. And from here, we're just going to do something a little different. We're going to change this so we get a positive rate, because this is going to help us solve here. A positive rate of our concentration with respect to time is equal to negative K. Now, what you have to understand to make this work, to how we get our integrated rate laws, is you have to understand a little bit of calculus. Now I'm just going to draw a little graph here to illustrate this. If I have some function, and this function goes like this, this would be x to the third. Now I know it's a very bad drawing of x to the third. This should kind of be more like this, right? Maybe I'll redraw it. So if I asked you to find the tangent slope at this point here, well, you'd say it's 0, right? Because the rise over run at this point is 0. Right? There's no change in Ry over change in time. But in calculus, we explore this idea of finding the slope of this at any point. So if you wanted to find it here or here, you could find it. And I'm just using the 0 so you know that it's 0. You can use the idea of a secant line to find a tangent line. Now, a secant line intersects the graph at 2 points, whereas the tangent line intersects at just 1 point. And in this case, it's right here at 0. And it's going parallel with how the graph is going, and in this case, that is 0 for a slope. Basically, in calculus, we say, okay, well, let's take a secant line. What's the slope of this secant line here? Well, it doesn't really match the tangent line yet, right? It's positive and it's not 0. Okay, well, what happens if I made it closer? If I brought that secant line halfway? Well, it's going to be a little more accurate than our other slope. So I'll just draw that here just to visualize. Now what if I brought it here? Well, now it's even more accurate. And now let's take the leap. What if I brought that point so infinitesimally close to our point at 0, 0? Well, there's basically no change. Even though there's like a very, very, very small change. This is the idea of a limit. What is the limit as we bring, what's the limit of the secant line as we bring that point super, 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 super close? I'm talking, let's just overlap them at this point, just for the sake of argument. Well, then the secant line, right, these lines that we're drawing with respect to the green dots, is going to match the tangent line. And this is how we find the slope of a tangent line at any given point. This is helpful in application to rates because, for example, rate equals k, and we got this formula here. Well, what we can do now is say, okay, so instead of going 1 second, 2 second, 3 second, 4 second, maybe making that interval of time seconds or minutes or years or days, let's make them infinitesimally small units of time, basically 0. Now, I know that can be a little hard to wrap your head around. You're like, well, how can it be 0? It's not 0. It's just so incredibly small. It's such a small change in time. So, so basically what this is saying is a d in calculus just means a very, 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 very small change. So we're basically saying a very, very, very small change in concentration over a very, very, very small change in time. I don't know why I don't know why I did that. Don't do that. It's not, you're not supposed to have brackets there, but over a very, very, very small change in time is equal to negative k. Now we have what's called a first order differential equation. Basically, when you have a derivative, which is dA dt, which you'll learn about, is equal to negative k. All right, and how we solve this is we're going to use this idea of differential equations called separable first order differential equations. Basically, we get these very small change in units on each side, and we take an integral with respect to each side. So real quick, I'm just going to erase a bunch of stuff and rewrite because we need to get rid of this graph. It's going to take up too much space. And my drawing software is not very good, so it's going to take a second. So let me just rewrite this. Let me pick red. Thank you. So again, I'm going to be as thorough as I can. A very small change in concentration over a very small change in time equals, oops, that's not where I should have drawn that, equals negative k. I did it again with the t, dt, not d concentration t, dt. Jeez Louise. Okay. So we're going to move these partial bits onto each side. That's going to help us solve. And for those who have never taken calculus, this will make 0 sense to you. And that's okay. You'll learn this in college. So dA equals negative k dt. Now, when you take an integral with respect to a variable, you can't have other variables. And a lot of people that may take calculus may think, oh, k is a variable. We're going to have to do some weird thing with this because it's just going to give us something weird. Well, don't be alarmed because k is a constant. It's like pi or e. It's just not defined as a value yet because we haven't been given context. K is that rate constant, which we'll find. It could be 1, 2.50, pi, something like that. We just haven't found it yet. So we're going to take an integral on both sides. So dA is basically saying take the integral with 1 with respect to concentration. On this side, we're saying take the integral with respect to time of negative K. Well, this is actually really simple. This side will become A, or our concentration, is equal to negative KT plus C. That's just how integration works. If you have 1, you add a t, right? Because the derivative of t is 1, or the derivative of negative kt gives you back k. So you're basically undoing the derivative here. And again, it will make zero sense if you've never taken calculus. I just want to be as thorough as I can for those who haven't. It's a very important class to take, so please take it if you can. Now, this plus c here is arbitrary. Basically what this says is, if I have a function that is this. So now we're going from rate to function of concentration that we can plug time into and get out of concentration. This gives us a family of curves, so to speak. Basically, if I have a parabola, well, if that plus c is going to change our function, it could be like this, or like this, or it could shift us down like this, or like this. So it follows the same trajectory, although we're just kind of shifting it up or down. That's what the c part's doing. It's basically equating, because when we take the derivative of this, so d dt of this side, this c just gets lost, right? So we don't know what it is. Well, it helps us in modeling, because let's find c. If we plug in 0 for time, this will cancel, because a 0 time times negative kt is still 0. So basically at time 0, our concentration is our initial concentration. So that's what c is equal to. Basically it's saying just add whatever your initial concentration is. So if we write this out, our concentration final is equal to negative kt plus concentration initial. And this is really helpful. We can find the concentration at any point in the reaction. Any point. 0.3 seconds in. What is the concentration? Well, assuming you know what your initial concentration of the reaction was, I put 0.5 moles of, or 0.5 molar of iron in. Okay? Or A, component A, I should say. You put 0.5 molar of iron in. That deals with this. Okay? You know what K is experimentally, you figure out what K is. Now you just plug in a time and you can find the final concentration. That's beautiful. And for a 0th order rate, where concentration does not matter at all on the rate of the reaction, you can find the concentration of the reaction at any time using kinematics. Hopefully this was helpful here. If you found this episode helpful, please check out then my first order and second order videos, where I explain kind of the math behind that and how we get these things, for those who have not taken calculus, or maybe if you've taken calculus. So thank you guys a lot for watching. Bye-bye.